Good day and welcome back to the second part of our discussion on integrating rational functions using partial fraction decompositions. So our previous video was a bit on the longer side, but there was a lot of information to get through in terms of reminders for partial fraction decompositions, and then we really needed a nice concrete example to tie everything together. So because of that, I'll hopefully make this video a bit on the shorter side to balance it out. So let's go ahead and use that information from our previous discussion to find a partial fraction decomposition of the given function, and then finish up by using that algebraic tool of the partial fraction decomposition to integrate the rational function. So a quick reminder, this is what we would refer to as being a proper rational function. It's a polynomial over a polynomial. The degree in the top is smaller than the degree in the bottom. As long as we can factor the polynomial in the bottom, we can write out the form of the partial fraction decomposition. And here it factors quite nicely. It's x times x squared plus 4. We have a linear term and an irreducible quadratic. And remember, an irreducible quadratic is essentially just a fancy term for saying it doesn't factor into smaller linear pieces. So our first step towards getting the PFD is to write out the form. So we have 2x squared minus x minus 4 over x times x squared plus 4. And each factor of that denominator is going to contribute to a term in our partial fraction decomposition. And at this point, I would like to suggest that you pause your video and write down what goes in the numerators. I just want to make sure we're all on the same page. So the linear term is balanced out with a single constant. Irreducible quadratics are balanced out with a bx plus c. Now, following our previous approach, we clear fractions by multiplying both sides by the denominator on the left. That gives us a 2x squared minus x minus 4 on the left. On the right, the x's cancel in the first piece, and the x squared plus 4 cancel in the second piece. And whenever it's possible to substitute in an intelligent choice of x, we do so immediately. And in this case, we most definitely have an intelligent choice we can substitute in. If we let x be equal to 0, the bx plus c term vanishes. And if each and every x term becomes 0, our equation is now minus 4 equals a times 4. So a in this case is minus 1. Now unfortunately, because of this irreducible quadratic, there's no other single value of x I can substitute in to immediately determine b or c. What that means is we continue on with our secondary approach, which is to distribute through and combine like terms on the right. So we would have ax squared plus 4a plus bx squared plus cx. And if we combine together the x squared, there's a plus b of them, cx, and 4a. And note, this is all equal to 2x squared minus x minus 4. And the only way two quadratics can be equal to each other is if each and every coefficient is equal. So from the x squared terms, a plus b is equal to 2. But if we pause here for a moment, we know that a is equal to minus 1. And if a is equal to minus 1, what is b? It's 3. Comparing the coefficients of the linear term, minus 1 on the left is equal to c on the right. And well, we now know a, b, and c. What we've determined is the partial fraction decomposition. So substituting in the values for a, b, and c above, we have minus 1 over x plus bx plus c all over x squared plus 4. And this is what we would refer to as the partial fraction decomposition of this proper rational function. And now that we've found the PFD, we are in an ideal position to integrate this rational function. And it's also worth noting that the typical question that we might ask you is not necessarily to find the partial fraction decomposition, but instead we would just say evaluate the integral. And in order to evaluate the integral, you would need to do all of this wonderful algebra to the side to rewrite it in this more manageable form. So let's go ahead and integrate. If we break it up into 3 separate pieces, we'd have the integral of minus 1 over x plus the integral of 3x over x squared plus 4 minus the integral of 1 over x squared plus 4. And individually, we can anti-differentiate each piece. Minus the natural log absolute value of x plus 3/2 the natural log of the absolute value of x squared plus 4. And note, how did I integrate that? With the substitution. So if that's something from our experience and practice you look at and you recognize what the antiderivative is, that is perfectly fine as long as you are correct. But never hesitate to include those extra details. So in this case, note du would be 2x dx. So x dx above would be 1/2 du, which is where this extra 1/2 comes from out front. And the remaining integral actually has a common form. Let me remind you that we previously integrated 1 over x squared plus a squared. It was one of our common anti-differentiation formulas related to inverse trig functions. And just to see if you remember it or not, maybe pause the video and see if you can write down this formula. What it is equal to is 1 over a arctangent of x over a plus c. So in our case, note 4 is 2 squared, so our a value is 2. And we're left with 1/2 arctangent of x over 2. And this completes our current example. And I do want to note that this is a very standard example involving integrating rational functions. And the only way we're going to be able to integrate a rational function, such as the one that we're given here, is using this algebraic tool of finding the partial fraction decomposition. And you can probably guess what I'm going to suggest at this point. We are in a great position to go to those suggested problems and at least practice a few of these partial fraction decompositions, as they are an absolutely essential step when we integrate rational functions. So we will continue this discussion in our next video by looking at some improper rational functions. Stay tuned and take care.